presentation on the cosmic microwave background, or the cosmic background radiation. So, it was actually an accident when this afterglow was detected at first, when Penzias and Wilson in the 1960s created a microwave antenna at AT&T's Bell Laboratories, and what they found was perplexing, which was an unexpected background noise like radio static, which they just could not get rid of. They took apart all their equipment and were very confused, and they eventually concluded that this was coming from space. This ended up winning them a Nobel Prize and allowed us to have a definition for what is now known as cosmic background radiation. So, textbook definition is microwave radiation coming from all directions that is the red-shifted afterglow of the Big Bang. In simpler terms, radiation usually only comes from one direction at one time at its strongest, though cosmic background radiation comes from every single direction all at once, meaning it's isotropic and quite like a comfy blanket for the universe. This blanket's really cold. You would not want to sleep in it, as it is at 2.725 Kelvin or negative 271 degrees Celsius. And usually, temperature in the cosmic microwave background does not vary too much. And it is actually similar to black bodies in temperature at 2.73 Kelvin. Though, because this radiation is so cold, it's actually invisible to the naked eye. And that is why NASA in 1989 created something called the Cosmic Background Explorer, or COBE, and he essentially allows us to see and observe and study this radiation.
The universe started literally with a big bang of hot, dense gas 13.8 billion years ago, and it has expanded and cooled ever since. This timeline shows the cooling of the universe since the Big Bang. Notice the timescale is distorted so that in the first second the temperature dropped dramatically during a brief period of rapid inflation, and protons formed from elementary particles called quarks. Until 380,000 years later, the universe was a hot, dense, and opaque plasma. Photons were scattered and could not escape the plasma. By then, the temperature had dropped to 3,000 degrees Kelvin, a period called recombination because electrons became bound to protons to form hydrogen. At recombination, the universe became clear, and the photons were released to travel about the universe. This is the CMB coming from all around the universe. As space-time expanded and the universe cooled, the wavelength has increased in accordance with Wien's law. Today, the temperature of the CMB has fallen to about 2.7 degrees Kelvin, 13.8 billion years after the Big Bang. This blackbody spectrum shows how the wavelength increases as intensity decreases from the maximum. And this COBE satellite data shows that the CMB is a blackbody spectrum, confirming the Big Bang theory that this universe began as a hot, dense blackbody. This analysis of CMB data reveals the composition of the universe. And finally, here's what it shows. Ordinary matter is only 5% of the universe.
Mr. Kraj, and I'll be talking about a couple of different images of cosmic background radiation. So let's start off with some basics. So images and maps of cosmic background radiations are useful to scientists because it helps explain how early universe was formed. This image of cosmic background radiation is from the Planck mission. It shows the different temperatures. The red spots, as you can see, and there are blue spots. So the red are for warmer areas and the blue represent the cooler areas. The different temperatures that are measured are extremely small. That difference may be the reason why the universe exists today, and I'll talk more about that in a bit. Scientists use these small fluctuations of temperatures to learn about the origins of some galaxies and stars. The remaining heat left from the Big Bang gives scientists an opportunity to examine it and provide us with information on the age, size, and what the matter the universe is made up of. Like I mentioned earlier, the blue spots are cooler and are also more dense compared to the red spots that are less dense. In the textbook, it explains that areas become warmer and cooler because photons had to expend energy, quote, to escape the gravitational force exerted by the surrounding gas. This resulted in photons to lose energy that caused the difference in temperatures. The point of the map is that it measures very small temperature differences in the radiation, which correspond to density fluctuations in the CMB at the time of recombination. These density differences are what permitted matter to be gathered by gravity, which is how the stars, galaxies started to slowly form. If the universe was perfectly uniform, it would still be a huge dust cloud. So the difference in density was significant in the formation of stars and galaxies.